But the ample problem,
Yeah,
does it have to be 3?
no,
Okay.
you do not have to have 3 states. In fact, this solution, I think, needs 4.
4 states. Did it work with 2 or is that too?
It will not work with 2. Yeah, for each one of these types, there's a minimal DFA. That is the minimum number of states that are needed to make it work, but you can expand this to be an arbitrary number of states. I could make a 100 state DFA to solve this problem, and it would be many unnecessary states, but it would still technically be a correct solution. Maybe I'll talk about how I could expand this uselessly so that you can get a sense of if you're doing something like that in the future and be able to recognize it. So we have a homework out. It's due next Wednesday, so 6 days from today. There are 19 problems, and if you know what you're doing, it is moderately difficult maybe, and if you don't, it will take quite a while and some back and forth between me and you. So my recommendation is please get started on it early. I have plentiful office hours, and if the office hours that I posted don't work, please let me know. I would much rather meet with you and get those questions answered early, get you off on the right foot, rather than have you procrastinate it till the last minute, realize it's way harder than you think it is, and then not have something that represents your best work at the end of it. My goal is that regardless of how much back and forth we need to do to get you to where you're satisfied with and where you can get a grade that you're happy with on the assignment, regardless of how much work that is, you can figure that out better if you start early and come talk to me and see me. I would be happy to work with you. Last couple in. All right, so who thinks they have a good solution for this from yesterday? 2 people? I know I verified it more than that. 3 people, I know I verified more than that. So there are some people out there who I know have a solution. But a solution to this, let's go over one of those, would look something like this. So here is a 4-state solution to this problem. We have states Q0, Q1, Q2, and Q3. Let's talk a little bit about this diagram. So from Q0, which is our starting state, on an A, so that's the first half of that prefix that we are looking for, the state Q1 represents we've seen the first half of that prefix. If we see a B from there, then we know, regardless of what comes after that, we've seen the prefix that we need, so we can loop back on that final state, regardless of what comes after that prefix. On the other hand, if we start with a B from the very beginning, we're looking at, well, there's no possible way for the prefix AB to happen if the first character we see is a B, so we're going to go to what we're going to call a trap state, or as I like to joke about, an Akbar state. I just imagine drawing a little Admiral Akbar in there with a dialogue that says it's a trap, and what happens from Q3 is no matter what you see after that, you see that B, there's no way to get the prefix AB. So regardless of what happens for the rest of that string, this is kind of a black hole. You cannot escape Q3 once you are in Q3. The only other way to produce something is to go AA, which is not the prefix AB. And if you have AA, there's no way to ever have the rest of that string produce the prefix AB to that string. So once again, we find ourselves in that trap state. So we either see the prefix and it doesn't matter what comes after that, or we don't see the prefix and we end up in a trap state. Questions on that construction or something anything I can clarify about this diagram, what it means, what the states mean, what the arrows mean?
So just clarifying, normally from each one of the states, it has to have 2 arrows leaving it, one for A, one for B. But in the case of Q3 and Q2, that looping arrow with the A, comma B is indicating that it doesn't matter, right? Because at that point, it's it isn't gonna make the cut.
Yeah, and you can do this in general, you can add a multi-edge like this, where you say you take this edge on multiple different symbols, and that's okay. You don't have to draw different separate arrows, one for A, one for B. You can if you'd like to, but now that you've seen something like this, you don't have to do that. It is the equivalent of that, though. So yes, exactly 2 arrows must leave each state, unless it's a single arrow that is a multi-edge for 2 different symbols. But 2 symbols, you need to define what it means to read a symbol from each state. So from Q0, there's an edge out on an A, there's an edge out on a B. From Q1, there's an edge out on an A and an edge out on a B. From Q2, edge out on an A and a B. Q3, edge out on an A and a B. That means that it's a complete DFA. Every DFA will need to have that, an out edge for every character that could possibly be in the string. So if there were 3 characters here, there would be 3 edges out per vertex. If there were 52 of them representing capital and lowercase letters in English, then you would have 52 out edges for every vertex. I won't make you do that. Other questions?
Is that the only basic rule, overall rule for DFAs?
Yeah. Well, for the construction of a general DFA, yes, but in order to be correct, it also needs to 100% represent the language that we are trying to represent, meaning that when you see the prefix AB, you end in a final state. When you don't see the prefix AB, you do not end in a final state. And that would be a correct DFA for this problem. But yeah, this is the entirety of the construction of a DFA.
Is there a rule for the amount of edges that go to a certain vertex?
Nope, can be arbitrary. It really won't be 0 because we need a way to get there. But other than that, there is no rule defining the number in edges. Great questions. Ready for another example problem? Okay. A DFA on all binary strings that accepts anything unless we see the substring 001. As soon as we see the substring 001, we're going to reject. But we're going to accept anything else. This substring can appear anywhere in the string. It can start with it, can be randomly in the middle, it could end with it. Spend a few minutes on that, talk to your neighbors, see what you come up with. We have a good question in chat about how many vertices do we think this needs? Does anyone have a guess at the number of vertices that you're thinking about on first pass? You don't have to be right, but what's your initial design? 3. 3 is a good guess.
Or no, it's like, would it be like 4 to check every number and then the last one to the end slot?
My solution has 4 vertices.
Quick question, we have to name like the states in any particular order? Like,
Not necessarily. So we've gone with the Q0, Q1, Q2, but as I think I mentioned this yesterday, it does not have to be like that. I like to name things if there's a reason for each of those vertices. You can absolutely name them something that represents what that vertex means. So for example, in here, if we see the first 0 that could be part of a substring 001, but also could be some other, maybe we see 0, 1 or something of the sort. When we see that first 0, we would need some state that represents, we've seen the 0, but we haven't seen the 0, 1 yet. The ending 0, 1 of that substring. So maybe you want to name your vertex something other than Q1, maybe something like 0, representing I've seen the 0, the first 0 of that substring.
I mean more like, do I have to name them in like, does Q2 have to be the end, or can I say Q3?
Yeah, it does not matter. All that matters is that the names are distinct and that those that are ending have the double circle for the final state.
Are you implying that we can have multiple final states?
We can have multiple final states. And in fact, you may want multiple final states in this particular example. Because we want to accept everything except for this substring. So yes, you may have an arbitrary number of final states.
I got it the other way around. I was really trying to find that.
In fact, I would argue that maybe there's only one non-final state here. When we see that substring, we want to say, make that the trap state. And as long as we end the string and haven't reached the trap state, then we accept. So every other state would be final.
Did you say we have like? I didn't remember listening, but did you say like we have multiple end states or just one?
Any number of final states.
You have an edge that returns. Actually, never mind.
I think I know what you were saying. And yes, you can have an edge that returns back to a prior state. Was that the
No,
question?
I was gonna,
That's my question, that's okay.
Yeah, totally fine. I do not think you can do it in 0. Although you have a solution that's fewer than 4, I'd be very curious to see.
it's just one.
Yeah.
Can you have more than one edge going from a vertex to another one?
Yes. Oh, yes. Yeah. There'll just be like a multi-edge.
Like if I had one edge going, I could do that.
Yeah. And it doesn't necessarily have to be going back to itself. You can have a multi-edge going from any vertex to any other
So if you
vertex.
do the multi-edge, is it kind of like an or statement?
Yeah,
Okay.
yeah.
Oh, yeah.
Is there like a handshake limit where like the number of like edges in your DFA has to scale with the number of elements?
Yes.
There's.
Yeah, you can come up with a function of the number of edges that are going to be in the DFA based on the number of vertices and the number of characters in the associated alphabet.
It seems like.
For each vertex, we need an outgoing edge for each of that, so it's just you just multiply the number of vertices that you have times the number of characters in the alphabet, and that's the number of edges we need to have. Although a multi-edge would count as multiple edges. Raise your hand if you're still working and would like some more time. A little bit more, a little bit more time. If you think you have an answer and someone else next to you thought they had an answer, verify with them and see if you have something that is the same or equivalent.
Yes. Oh, yeah. And then everything goes back to the start. Yeah, that's pretty. Your trap piece at the start? No, my trap sticks. Okay.
One thing you might want to verify if you're in the process of verifying, does this work for something like 0000001?
That's one that screwed me up.
I mean, it's just, I mean, it's just checking if it like doesn't, or like, this is checking, oh wait, yeah.
Another good one would be 01001.
Oh boy.
Now you got 0. Yeah. Well, I just think about it. It leaves you for sure. The moment like that, so you have that still one.
Yeah.
And then all the rest. Oh, you're right. You just try to figure out just. This there. All the rest of them pass. Basically, if you get 2 zeros at all. Oh, you're right. This has once you get 0 zeros. This is essentially. Otherwise, if you get 2 zeros, you're gonna have any ones that.
Yeah, okay, so
Nice.
Oh, 0, 1.
So there's that.
So there's every 2 zeros at any point where you can't continue from back supersede 2 with 8 or 0. You have to hit the traps. Because even if you go 0, 0, infinity, inevitably you're gonna hit another 1. And that substring doesn't exist for this.
Unless it ends with a bunch of zeros.
In Q0 be in the final state.
Yes.
Okay.
Yeah, your starting state can be a final state. Which is something we want for this because the empty string is accepted. The empty string does not contain the substring 001. So it is a sentence in this language.
How do you verify something like this? Again, obviously, you can't just like sit here and just.
Yeah, you're gonna have to come up with a counterexample or make sure that. So I would think of this substring 001. Think about all substrings of length 3 or even of length 4 and make sure that it works for everything within those associated substring lengths.
Yeah. That's about here.
Oh, yeah, you're in the 101.
This is 101.
This goes
Right.
one.
Oh, yeah, I'll see that.
Ready to see an answer?
Yeah.
Here's my solution. Notice that I've named the states something other than Q0, Q1, Q2, and they are related to how much of that substring we've seen so far. This is perfectly valid way to draw a DFA. Those names just need to be distinct.
There's 0, 0 state. You move the 0 back because you're only considering the last 3, so you're not really changing anything in your state. Is that
Right,
correct?
yeah, you've still seen the 0, 0 part of that substring. If you see 0, 0, 0, 0, 0, 0, 1, that contains the substring 0, 0, 1.
So basically, if you see 2 zeros, then it can add to 1 ever. If you see any sequence with 2 zeros, you cannot have any ones past those 2 zeros.
Well, yeah, and except, yeah.
Did you mention there was a program that we could use? To
Yeah,
draw these
to
better?
draw these,
You
yeah,
mentioned it,
yeah,
what is it?
JFlap. Yeah, it's linked in Canvas and the Canvas modules. Sorry? I have not looked into it. If not, that would be a fun project for the quarter.
Source project.
Yeah. Any questions on this diagram or the differences between what you produced and this? Verification that what you produced is also correct? How are we feeling about DFA construction? How do we, show of thumbs, we feel like this is making sense? Need more practice with it? I don't really know what's going on and could use some assistance. So I think that anyone who's here, you're ready to plow through the homework. Anyone who's here, start the homework, ask questions as you are in the process of doing that construction. And if you are here, then this is probably something that we should talk about in office hours. I would love to see you and we can get some further examples, maybe either pulling from the homework or from some of the other problems in those lists of problems that aren't part of the homework. That's why I give all those extra practice problems as well that are pulled directly from the book so that you can do additional practice if needed. And then it gives me something to pull from for examples to work through in office hours as well. All right, we are going to talk about another way to express the same class of language that a DFA can represent. So a DFA has limitations in the kinds of languages that it can represent. But as we talked about, DFAs accept some language, exactly one language. We're going to abstract this a little bit and think about the class of languages that the concept of a DFA could accept. What is that limitation? We can call these a family, representing just some set of languages or a class of languages, some family of languages that we can use this tool to represent. So first and foremost, family of languages accepted by any DFA. I already accidentally spoiled this, but it is limited. Can anyone think of the dividing point? Like, what is something that a DFA could not represent? What is the difference between something a DFA could accept and something it couldn't? It boils down to storage. Basically, since a DFA does not have storage, whenever you would need to store some information to recall later, a DFA cannot represent that. It's the state that you are in is all of the information that you have. And note that the state that you're in does not store any kind of history about where you've been, about the symbols that you have read. So imagine trying to solve some problem like recognizing a palindromic sequence. In order to represent a palindromic sequence on a single pass through a string, you would need to store the sequence of characters that you've seen so far so that you could determine a middle point and map them back to be able to say, yes, that was a palindrome, or no, that was not. There is no DFA that you could construct that would represent a palindromic sentence. So that kind of represents the boundary of what a DFA can accept. So we're going to call this class of languages regular. A regular language is a language that a DFA can accept. A language that is non-regular is a language that we could not construct a DFA for. That said, if I asked you to prove that a language is regular, how could you do it? Draw a DFA for it. Yeah, exactly. It's not a complicated proof. Draw a DFA. If that construction is possible, you have proven that that language is regular. It's worth practicing because this is how we are going to prove this. It's significantly easier than what we will talk about in a week or so, which is how to prove that a language is not regular. That is much, much harder. All right, time for an example problem. Another example problem. So you might see a question worded something like this. Show that a language is regular. And now we have one tool, a way of being able to show that a language is regular. Draw a DFA for it. It's exactly the same question. So if a textbook question asks you to draw a DFA for this language or show that a language is regular, you can do both of those by drawing a DFA for it. So what this says is the language is AWA. So the character A starts and ends the string, and in the middle of this is some string W. And W can be anything in the star closure of the alphabet AB. So it could be empty, it could be full of anything else. So let's draw out a couple of examples. What's an example of a string in this language? AA. Great. What's another example? Sorry? ABA. ABA? That's in the language. What's another example? AAA. AAA? What's an example of something not in the language? B? How about ABB? Not in the language. So come up with some kind of, yeah, question?
What's the star?
This is the star closure of that language.
It
So
does not accept the empty, or
this can be empty, but it's just the W that's empty. So AA is A followed by an empty W followed by an A. Yeah,
Is A by itself in the language?
no. So we need two copies of the A here. It needs to both start and end, and they need to be distinct. Yeah, I think that's the clarification I need to make on the wording that I said, is that it starts and ends with an A. A single A does start and end with an A, but is not in this language. So yeah, let's actually draw that up there as well as a, no. Yeah.
How do you know if the W is empty? Or what tells you that it's empty?
So this is the construct, this is just concatenation of, so we need the character A followed by something or nothing in this star closure. This can be an arbitrarily length string of any A's and B's, and then we need to see this A at the end. So the W in this case, here the W is lambda. Here the W is B, here the W is A. And for anything not in the language, then it's not in that structure anyway. But we could also do something like A, B, B, A, B, A. And that's in the language, and W would just be everything between that first and last A. BA is not in the language. Commonly forgotten aspect, drawing that arrow pointing to the starting state. That's something that will be a very small deduction on something like a homework, but it's something that you absolutely need as part of a DFA. First conclusion we can draw, if it starts with a B, there's no way for it to start and end with an A. So we're going to, on a B, transition to a trap state. A represents the starting A. What do we want to do on a B?
Perhaps go back to A0.
If we went back here, that would say we haven't seen the starting A yet. If we see AB, it's still part of a string that could start and end with an A, but we haven't seen that second A yet. So if this state represents, I've seen the first A, but I've yet to see the second A, we could have B loop to itself. If that ended the string, we still haven't seen that second A that we need to end, but the state's not final. So it doesn't matter if we end here. What about on an A? Go to a next state. Should that state be final?
Yeah.
Yes. AA is in the language, so we want to make sure that when we see AA, that that particular state is final. However, there's no guarantee that this is the last A in the string. So from Q3, what happens if we see an A?
People can go back to Q3.
Loop back to Q3? Great. Question?
Would that Q2 work even if you had ADA?
We would say A, B, A, and then the W for that is just the B, which is in the language, and we would end up in this final state. Great question. What do we want to do from Q3 on our B?
Go back to two.
Back to Q2? Because now we haven't ended with an A, so we shouldn't be accepting at this point. But there's no guarantee that that's the last character that we've seen. So we'll continue as long as we see B's to loop back to Q2, but when we see an A again, as long as that's the last thing we see in the string, we're back to Q3. See more A's? That's fine, as long as one of them is the last one. As soon as we see a B, we go back to Q2. So this is complete. Question?
Would Q0 or would the Q0 to Q1, could you erase that and just do Q0 back to with just like a return with B? Would that work?
No, because then if you had something like BAA, then it doesn't start and end with an A. It would start with a B. As soon as we see it starting with a B, we cannot, there's no such string that we would ever accept. So we have to go to a trap state. But if it starts with an A, there's no way to know that it doesn't end with an A until we reach that last character. In which case, we would be ending on a B or a B and be in Q2. So basically, if the string ends with a B, we'll terminate in Q2, a non-final state. If it ends with an A after it started with an A, then we'll terminate in an accepting Q3. Questions on that? Just kind of seeing the logic of drawing it out help a bit. I try to, when I have different examples like this, try to solve them in different ways. Let you reveal an answer and then talk about it, and also go through the actual construction itself so that you can see the logic that I would use when I construct this.
So Q3 is the only final statement.
Yes.
So. I don't really know how to phrase my question, I guess. If this thing was like left to run on its own, is there some other thing that indicates that it has to cycle until it reaches Q3 no matter what thing?
No, yeah, I think so. So
Like it can't end on Q2.
it could, as long as the termination point is when we're done parsing the input string. So if the input string was this long string right here, we would go from Q0 on an A, B, B, A, B, A, terminate. And where we terminate at the end of that string, whichever state we are in, determines whether we write a check mark or whether we write an X.
Okay.
On the other hand, if we had A, B, B, we would have A, B, B, terminate. And since this isn't an accepting state, that's why we write that X. We don't accept because we did not end in a final state. Great question.
So basically, any final state in this case has to have an inward flowing A, right? That's.
Yeah, for this problem for sure. Anything else? Moments to digest this, because this is not particularly easy. Everyone have what they need from the board for this? I'll reveal something that looks probably something like this. I actually don't have what was on the slide here, so I just came up with this off the top of my head. Yeah. Remember that L squared in this case is just a language concatenated with itself. So what is L squared? Close, but not quite. Because they don't have to be the same string. We don't want to use exactly the same variable for this. We want anything that would have been accepted from that language to be the first half, and anything that would have been accepted from that. So W1 and W2 can be the same thing, but they don't have to be. So go ahead and construct a DFA representing this language. You may want to refer to the solution to the last one as part of this construction.
So the W1 and W2 don't have to be the same length, right?
Correct.
So
Yeah, the
can
first one may be empty and the second one may be 100 characters.
can either W1 or W2 contain substring AA in it as well?
Yes.
Uh,
Yeah, so maybe we have 10 consecutive A's. And we decide that the first two A's has W1 as lambda, and the second W2 is 6 A's.
But there has to be two A's in the middle.
Yeah, we have to have 4 total A's now, at least, in this string.
So like A, B, A, B, A would work. So like A, B, A, B, A would.
Correct. Six. No, we don't. We can leave 5. No, you need 6. Yeah.
Yeah, it's basically just the same structure. applies, right? Yeah.
That is something that I was planning to ask right at the end of this was, well, if L is regular, will L squared always be regular? The answer is yes.
Any number of concatenations?
Yep.
Are regular, okay.
Although if you wanted to get all of the associated, so something like the language star closure, so L union L squared, union L cubed, union L to the fourth, that would be impossible. Because then how many concatenations, where does that stop?
Yeah.
So you could, if you put an arbitrary endpoint on that, then you could make it right. Is right. You could make it. The power is not in your hands. As much as we wish it were, not in my hands either. Logic is the way it is. Unless, of course, you want to assert that you can change logic. Narcissists like
That's called gaslighting.
Yes.
I can change the logic, but the logic would be illogic, so therefore, by proof of contradiction, I cannot.
But I'm right and you're wrong. Yeah, that argument never flies.
It does when my wife does apparently. With 8-dimensional logic she's working on, but this is bogus. Doesn't matter if I'm right or if she's wrong, if we're both wrong, she's somehow always right.
All right, let's quickly go over this because we don't have a ton of time left for this. We wanna try to draw it out, or do we want to reveal it and look at it? Any preferences for that?
Draw it.
Draw it out. That was more useful. Let's do it. I'll try to be quick because we don't have a ton of time. So we said before that we were going to, on a B, go to a trap state. We're gonna call that Q1, that loops to itself on an A or a B. So once we see that first A, we're going to map basically that we are at this A. So on an A, we're gonna go to some state that's gonna represent, we've seen this A. Now we need to be able to assert for something in W1 that we're going to assume that we're going to wait until we see this second A. So if we see a B in the middle of this, we're gonna loop back to ourselves. But when we see this other A, we're going to move on to say that, all right, we've seen this A. Great. So this A into Q3 now says we're finished with W1 and we've seen this A. Great. Now we're going to see this A. But we need something to do on a B here. What happens if we see a B here? I guess we already looped it. But when we see this A, what do we want to do on a B? You're not done. Something like that. Can we do A, B, A, B, A, B, A, B? That's fine, right? Because then there needs to be a way to go do that. Okay, maybe that will work. Let's see if we can poke a hole in it eventually if it's wrong. So we get to this point, now we need to tackle W2. So on a B, we can loop to ourselves again. That can be an arbitrary amount of W2, and then we see a last A, and this is going to be our accepting state. What happens from here if we see an A?
Okay.
We're fine, back to itself. If we see a B, back to Q4. Can anyone see a flaw in this? Is there any counterexample we can come up with? What about one more arrow? A, A, B, A, B, A, B, A, B, A, B, A, B, A. A, B, A, B, A, B, A, B, A. We've seen at least 4 A's at this point, so we should be accepting. There's a small issue with this B. How do we fix it?
Good try.
Now, you don't necessarily want to trap because we need to see these 2 A's in a row though, for sure. So yeah, if we see a B in between these 2 A's, that's a problem.
So B from Q3, Q4. Or not, sorry.
Yeah, so maybe we do actually want this to go to a trap state. Is there an issue with this?
Well, that B could probably go B.
Yeah, A, B, A. Or maybe A, B, A. Yeah, maybe this does work. Any counterexamples people can see?
Can Q1 go to Q0 if it's A or no? It would
Good.
just stay in Q1, right?
Yeah. Yeah, this is that trap state. So I don't think we actually want this. What do we do in Q3 on a B?
For ourselves. Q3, even though we're looking for the second A.
Yeah, the issue is once we see that second A, we need to see that third A.
You could just say that it's part of W1 though.
Right, you could say, but let's say that, let's structure this such that W1 is everything between the first and second A. And then we need to, I guess we need to be able to see that for sure, right? We don't know where these 2 A's are gonna come in, so it could be very much part of that.
The internal words, like word 1 and word 2 can be comprised of both A's and B's, right?
Yeah.
Yeah, okay, so.
The solution?
Even if you have a B going from Q3 to Q2, you're still guaranteed 2 A's in a row before you get to Q4.
Yes, so if we did something like move this back here,
Yeah,
again, so A, B, A, that won't work because we never had those 2 A's in the middle. We need to see that A in order to move into W2. So this was right. I just like to confuse people sometimes.
Crazy.
Yeah, that is the solution. That's what I have here. Kind of on top of it, but yeah, that's the same thing. I like to do this because this is the kind of thinking that you will want to do on your homework to verify that it is correct. So I also want to show you what it's like to logically go down the wrong path and then have to back here and go, wait, what is the logic to ensure that we have these 2 A's in a row? We eventually need to do that poly.
Because we need. Because even if we see it, it doesn't end in 2 A's.
Yes. We are very out of time. We will come back to, this is basically the end of the DFA set of 2 lectures. This should be everything on the homework with the exception of the NFA problems at the very end. We will tackle that tomorrow. So at the end of tomorrow, you should have everything that you need to do the homework. Unless I'm lying, in which case we'll figure that out tomorrow.
The NFA stuff, part of it.
I know, there is a link. The concept of non-determinism is consistent between both those items.
Yeah.